For what values of k and p will f be continuous and differentiable at x equals 1? This is number 4. Well, in order to show continuity, we have to use limits. In order to show differentiability, we have to show limits. Here, for continuous, we use f. For differentiability, we use f prime. So we'll start by saying the limit of f of x as x approaches 1 from the left. Now the reason I'm choosing 1 is because that's where they overlap. That equals 2 minus 1, which equals 1. The limit of f of x as x approaches 1 from the right. That would be 1 plus k plus p. And for continuity, these two must be equal to each other. So we know 1 equals 1 plus k plus p. This doesn't help us too much because right now we still have two variables. That's why we have the differentiability parts. So first we're going to find what f prime is. F prime is a piecewise function. Take the derivative of each. 2 minus 2x when x is less than 1. 2x plus k when x is greater than 1. So the limit of f prime of x as x approaches 1 from the left, that'll equal, plug in 1 into the derivative, you get 0. The limit of f prime of x as x approaches 1 from the right equals 2 plus k. Therefore, k plus 2 equals 0, so k equals negative 2. If I plug k equals negative 2 back into the original equation that I have, which is this one, then we know p is going to equal 2, and we are done. Part B, for the values of k and p found in Part A, on what intervals is f increasing? Well, we want to look at f prime then, f prime being positive. So f prime, we already found, was 2 minus 2x when x is less than 1. 2x, now we know what k is, it's minus 2 when x is greater than 1. So we better find any critical points to create a sign chart of f prime. So since I have two pieces of this, when does the first one equal 0? That would be at x equals 1. Oh, that's fine because that's one of my endpoints. When does 2x minus 2 equals 0? That's also at x equals 1. So the only critical point I have is 1. If I pick a number smaller than 1 and plug it into the first one, so pick a number here, plug it into here, I end up getting, like plug in 0, I end up getting positive. Pick a number after 1 and plug it into here. For example, 2. Plug in 2, you also get positive. What you notice really quickly is this graph is always going to be increasing because f prime is always positive. So that's what we need to say. Since f prime is greater than 0 for all x, f is always increasing. I want to go back up to points. Here, I have 1 point for the limit of f of x, 1 point for the limit of f prime of x, 1 point for k, 1 point for p. That's 4 points. In the second part, this is only worth 2 points, and that would be 1 for having pretty much all of this work, something leading towards a solution, and then 1 for the justification. Even though the sign chart is technically qualified, I was looking for work on this one. C, using the values of k and p found in Part A, find all points of inflections on the graph of f. Well, we better look at f double prime of x. The derivative of f prime, or the second derivative of f, would be negative 2 when x is less than 1, and it's positive 2 when x is greater than 1. I'm going to look at a sign chart of f double prime, but I notice I have an issue. I'm not going to have any possible inflection points just by taking the second derivative and setting it equal to 0, because that never happens. It either equals negative 2 or positive 2. And it switches at 1. So f double prime is always negative before 1, and f double prime is always positive after 1. Therefore, we can say there is a point of inflection at x equals 1, since f double prime changes from negative to positive at x equals 1. This one was worth 3 points, 1 for having f double prime, 1 for identifying x equals 1, and 1 for having a justification statement.